I conducted 2 lectures in the morning. Yeah, recording is
Yes,
gone.
it started.
It has started. Hmm, good. But none of the lectures could be recorded through MS Teams in the morning. Okay. So we have discussed on the idea of rectifiers and the rectifiers with filters, where we have discussed on half wave rectification and full wave rectification. In the full wave counterpart, we had gone through the idea of center tap transformer and the bridge rectifier. And we also discussed on the application of capacitive design in the corresponding rectifier, which leads to the idea of a filter. Okay, so rectifier along with filter aspect. So over there we had gone to the filtration scenario through which we understood that the corresponding DC current or the DC voltage level can be enhanced over there, and that enhancement is far better if we take into account the bridge rectification context, because that bridge rectifier happens to be the best amongst the three if we take into account the level of rectification that goes through. So we had gone through that particular lecture. Now just before I get into the regulator segment, let me first and foremost discuss this problem with you all. This will complete the aspect of the rectifier part that we have discussed, and obviously whatever is given in this corresponding module. Okay, I mean this particular presentation. This is the last page of this particular rectifier and regulator circuits presentation, 27 out of 27. So you can find out what the problem is given is you are having a AC input, peak to peak AC input, which is 230 volts, okay, RMS over there. So that is being fed at the input end of a transformer. This transformer is having a 5:1 ratio. So it means that at the secondary end, the corresponding voltage that will get developed should be 1 by 5 times of 230 volts. So the secondary potential RMS voltage should be 1 by 5 into 230. And that has been shown in the first line. That is RMS secondary voltage is 230 into 1 by 5. That happens to be 46 volts. Now, as you can check in the diagram, the same thing has occurred over here as well. But what is the difference? In this case of full wave rectification, it is the case of center tapping, as you can check over here. And in this case, there is no center tapping. So the entire secondary voltage is applicable to this corresponding Wheatstone bridge comprising of diodes. Okay, that we have learned in the context of bridge rectifiers. Well, owing to which what is coming into effect is this. If just a minute. So owing to which what comes into effect is this, that the maximal voltage at the secondary terminal when the in one particular half cycle, if I take into account, should be equal to 46 into root 2 for the entire one, and that divided by 2, which is equal to 32.5 volts. It is, I'm talking about the peak voltage. So RMS into root 2. So in that case, the peak voltage across the entire secondary is 65 volts for the first case. And because it is center tapped, the two halves of it is going to experience a corresponding peak voltage that is equal to 32.5. That is obvious. Now, based on that particular idea, if I apply these corresponding formulas for IDC and VDC, then we observe that the value of VDC, which is the one which is ultimately being disclosed in this particular problem, that is VDC comes to be equal to 20.7 volts in the context of center tapping. However, when the same design is being taken up in the context of bridge rectifier, what we observe is this, that the value of VM is the same 65 volts, as there is no center tapping over here. So the 65 volts peak is going to get applicable for this particular Wheatstone bridge, and the load resistance is connected over here, which is not shown, but it is connected over there. So if I want to understand what is the value of VDC, the same idea of 2 VM by pi. So if I apply the corresponding formula, we get the value equal to 41.4 volts. So we can understand that through bridge rectifier, the level of the DC voltage that we are obtaining finally across the load is far higher, almost double according to this example, okay, in the context of bridge rectifier compared to this case of uh, center type scenario. So that is the case. That is the advantage of bridge rectifier that gets explored to this example. Okay. So
Sir,
that yeah.
sir, in center tape rectifier, I think VDC is equal to VM by pi only.
No. We are talking about full wave rectification. It's not half wave rectification. So automatically that value should be equal to 2 Vm by pi only. But here the value of Vm is equal to 32.5. Here the value of Vm equals 32. The value of Vm is equal to 32.5, not 65. But in this
Yes, sir.
case, the value of Vm is equal to 65. Okay, that is the
So,
difference.
one thing to
So
ask, sir,
yeah.
in this PDF, bulk resistance has been discussed, or have you discussed
Now,
bulk?
bulk resistance, not in that sense. What we have taken into account is definitely load resistance. Now, that load resistance we can take into account as bulk resistance. That depends on the application. We talk about load resistance, and the load resistance value probably according to the example being given over here is 100 ohms R. Okay.
Sir, in that exam, bulk resistance, one question came. That's why I asked.
That is not an issue. That is load resistance or bulk resistance. It means the same idea. When we talk about the corresponding across the bulk resistance means across the load resistance. What is the ultimate output that you are going to observe?
Okay, sir.
So now let me tell you one thing. It may seem a bit confusing, but I would like to quickly skip to this particular presentation and then move on to this one for a detailed idea of this Zener diodes. Okay, I mean to be more appropriate, Zener diode regulation. But I mean, these two presentations, I mean, this particular presentation, which is right now on your screen, is designed for the case of basic electronics, obviously. And the one which I'm showing on the other half, that is this one, the add-on on rectifier and regulator circuits. In this segment also a Zener segment is there. This one is giving you an idea which is from a course, obviously not basic electronics. It's a course of analog electronics course. So from that particular segment, a part has been taken off, and accordingly, we are going to discuss on that part as well. Ideas are very similar, but the way we are going to look into the problem will be slightly different. Obviously, the basic idea is same in both the cases. We will check it out, what I am trying to mean over here. Okay. So at the very beginning, I would like to say that if you can recall, let me go back to this initial diagram. That will be add a diagram. So let's get back to the diagram. First page, yeah, in the first page itself. Now here, look at this initial diagram. In the very first class, this diagram was displayed on your screen, where from which we got the idea that the output of the rectifier, after being fed through a filtered circuit having a capacitive design, the output happens to be like the one has been like this one has been shown over here, indicating higher level of DC compared to the rectified outcome that we are having over here. The DC level is higher. So what we do next is this: to have a DC power supply, I mean, a kind of a power supply which should have minimum level of variation. In what sense we are talking about minimum level of variation? The minimum level of variation stands on the fact that is the input source voltage. If that varies, that will not change the output voltage of the corresponding circuit. Where the output voltage, by output voltage, I would rather try to stress on the fact that by output voltage we mean the regulated voltage or the DC voltage over here. And the input voltage can be an AC supply, which is coming from over here, coming from this end, input voltage. So the value of Vs, ultimately the regulator circuit, the input voltage means this one, which is also not pure DC, but it is having an AC effect there as well. So, but the initial AC line is this over here. And the point is this, that if you're having a variation of the input voltage at the input of the regulator, that will not affect too much. It will definitely affect, but it will not affect too much the output regulated DC voltage that we wish to develop. Okay. Similarly, if we vary the value of the load resistor over here, that will not also affect the level of the output DC voltage. Now there lies a particular point. Now the output DC voltage is clearly being shown over here in this diagram. This is a DC output, V out, that we want to have. So what I am trying to figure out is neither Vs, that is the input, Vs, nor the, sorry, This has started off. Just a minute. You please mute your microphone. So neither the value of Vs, neither the value of Vs, that is the input source voltage, okay, nor the value of this RL, which happens to be the load resistance over here, okay, none of these two components should be able, I should ideally be able to change the level of V out to an appreciable extent. So the level of V out remains more or less fixed. But obviously that is not possible. What the fact is this, that to a certain extent of variation of the input source voltage as well as the corresponding load resistance, the value of V out change can be encountered, and accordingly what we can say is this, that the regulated DC power supply is working perfectly even if there is a variation of Vs or variation of VRL or both. Okay, V out is not changing too much. That is basically called regulation. Now this regulator circuit that we're referring over here, this regulator circuit is being designed making use of Zener diodes. Okay, so let me get to that page. Yeah, regulator. So that has been clearly being mentioned in the statement that given at the top, that a voltage regulator regulates the voltage regardless of the adjustments in the input voltage or connected load. So that is what I was basically saying. Regardless of the input voltage Vs or the connected load RL, the voltage regulation will be more or less fine. Output will not vary too much. That is ultimately the idea of a regulator. So if I take into account Zener diodes are what are basically Zener diodes. We'll have a discussion on it later on when we are going to highlight mainly the difference between Zener and avalanche multiplication. Okay. To just stress on this particular fact right now, Zener diodes are special kind of diodes where we have very high concentration of carriers. What I mean is this, it's basically a PN junction diode only, but the concentration level of the dopants happen to be pretty high compared to the level of dopant concentration which is present in a normal diode. Owing to which the barrier that we have, that barrier height or the barrier potential is quite low, and because of that what comes into effect is a quantum mechanical tunneling of electrons come into the context. So it's not like that it has to overcome some potential barrier and then go to the other side of the junction. It's not that kind of an idea that leads to the concept of a Zener current. The concept of Zener current comes from the idea of quantum mechanical tunneling of electrons. I will talk about it in as far as short possible later on because it's a long story to understand what this quantum mechanical tunneling actually means. Okay, so what you have to understand at this particular point of time is this: Zener diodes do have a very high dopant concentration. First thing, and the second point is this: the corresponding carrier transport process that is effective in a Zener diode is through quantum mechanical tunneling of electrons, not the one which is encountered in the context of normal diodes. Okay, in normal diodes, it will be just like normal carrier path, I mean overcoming a barrier and all that we all know. Now this quantum mechanical tunneling of electrons and that leading to the idea of the Zener current IZ, that is mainly effective. I mean that particular concept is mainly effective when we put the Zener diode under reverse bias. When we put the Zener diode under reverse bias, mind it should be under reverse bias. Look at the information being conveyed over here, the corresponding circuit representation, circuit node representation for a Zener. Now you can find out that this is the anode and this is the cathode. Okay, so when we're talking about the reverse biasing of this particular Zener diode structure, it should definitely mean that the cathode will be at a higher potential compared to the anode. That is the way the circuit should be effective, made effective. And once that thing is made effective, if we have a Zener current, it means that the Zener has crossed its breakdown potential in the reverse domain. When we are having appreciable level of Zener current through the Zener diode, it should mean that the Zener diode has crossed its breakdown potential in the reverse domain, or the reverse breakdown potential has got exceeded. So what is the ultimate thing that we observe ultimately? What we observe is this, that due to a very very low variation of voltage, there is an excessive variation of current when the breakdown process has its effect. Okay, so let me just share this diagram that will make the idea far more clear, which is I think is it there in this slide? It's also there in this slide, but it's better. Okay, you first and foremost go to this one. I will show that slide as well, not to worry. So look at this presentation. This is the Zener diode. Okay, this is the Zener diode voltage that we're referring to, which is being mentioned as VZ. Why I am talking about VZ? VZ happens to be called to be the test voltage of the Zener. I mean, that is the voltage of the Zener which remains more or less fixed, and the current variation across the Zener is too high. And due to this more or less fixed value of Vz, what does it lead to? It leads to a DC level at the output. So this Vz is very important to get generated, that breakdown potential, and accordingly a test voltage where this voltage remains more or less constant, but current variation is too much. Yes, any question?
Sir, please explain. You have said at
I
this
will
particular.
explain. I have not finished yet, not to worry. So we have this particular concept that the value of Vz remains more or less fixed. Under reverse bias, look at the potential of Vz, plus on the top, minus at the bottom, indicating the diode is under reverse bias. Okay, so when we talk about Vz, we specifically mean that the diode is under reverse bias. Otherwise, when we talk about the putting the same Zener diode under forward bias condition, we should refer Vz as Vd, the one that we are already acquainted with. The representation Vd, that is a forward biased diode voltage, Vd. So Vz and Vd, in that case, it can be represented as Vd. Now the point is this, that why we represent it as Vd? Because under forward bias, the mechanism of transport of carriers in the context of Zener is very similar to that of a normal diode. The difference happens in the reverse bias only. What I was talking about, the quantum mechanical tunneling of electrons, because of which we are having an excessive rate of current flow through the device, obviously keeping within the limits of the power dissipation of the Zener diode. That's a separate story. But the point is, this quantum mechanical tunneling of electrons is far more effective in the process of current generation in the reverse bias context. And that phenomenon is very much different from the bypassing the barrier and getting into the other half of the junction for the corresponding majority carriers when we talk about the forward biased operation of the diode. Now, ultimately what stands is the one for the case that the ideal scenario has been shown on the left. The practical scenario has been shown on the right. Why I am putting it as practical? Because though it has been mentioned as ZZ doesn't carry any meaning. It should be from wherever it has been taken. It's a bit wrong. I mean, this ZZ should be actually RZ. Maybe ZZ is given in the particular textbook, wherever it has been taken from. But the point is this, I'm talking about a ZZ actually means what? Actually, the ZZ, or the one which we call as RZ, small r with a Z in the subscript, we mean that to be the corresponding incremental resistance of the diode. You all have studied about the resistance of a diode, the incremental resistance of a diode, the dynamic resistance of a diode. You have studied about that particular concept. I'm talking about that scenario only. But the point is this, the factor ZZ or RZ, whatever we say, that incremental resistance of the diode, I mean the Zener diode, is effective under reverse bias. So here we are talking about the incremental resistance of the diode in the reverse bias state. So if we consider that information along with the corresponding voltage source as being shown over there, then this combined representation is being represented as Vz. Okay. More to talk about it from the other slide, which I'm going to present. Okay. And if we quickly have a look at the difference between the Zener diode and the normal diode. So the one which is given on the left, this particular VI diagram is for the normal diode. And this is for the case of a Zener diode. Now, normal diodes forward bias operation and Zener diodes forward bias operation are almost identical. Almost identical, have got no difference. Okay. Where does the difference lie? Difference lies obviously in the reverse domain. Normally for the normal diodes, which we take into account with moderate concentration of dopants, in that case, the avalanche potential is quite high. However, when we talk about Zener diodes, the corresponding breakdown potential from where this sharp fall is occurring over here, this breakdown potential is at a much lower level normally. Okay. So that is the very quick difference that we can observe from these two graph representations. Okay, and the point is this, that in the quantum, this particular concept of quantum mechanical tunneling of electrons, which leads to this increase of current, this is far less detrimental compared to the case which encounters over here in the context of avalanche multiplication. In avalanche multiplication, the value of breakdown voltage is high. The current multiplication may be beyond the limit, owing to which the corresponding diode may burn out. So that is a very crucial factor. That was why if you can recall, we have talked about the fact you should be very much careful about the peak inverse voltage operation in rectifiers. It should not exceed the breakdown voltage, because once it has a chance of exceeding the breakdown voltage, it should lead to a condition where the diode gets burnt out. Because the normal we put up normally in the corresponding circuits, we put up normal diodes, because Zener diodes have got no different different advantage of putting up over there in the corresponding circuit. So we normally take up normal diodes over there. So this is just a quick idea about the difference in the characteristics between Zener and avalanche. This is actually avalanche representation. This is Zener representation. Looks very similar, but conceptually different. Okay, let me just show you to continue with the discussion on the VI characteristics from the other slide. This is also there in the MS Teams environment in this Ecc01 Am channel. It has been uploaded. You can check it out over there as well. So in this segment, look at the reverse bias operation which has been shown. We are having a VZ. Look at the polarity which indicates the reverse bias scenario, and the component IZ, that is a Zener current which is flowing through the Zener diode. Okay, so the power dissipation under reverse bias should be VZ into IZ. Very simple. Okay, now the model representation which has been shown over here, I mean, in this case, this particular case I am talking about, which has been shown over here, this one on which I am encircling right now. Okay, this has been clearly mentioned in this diagram. Look at this case. What are the components? This VZ is effectively equal to what? VZ is effectively equal to VZ naught plus RZ into IZ. Now I'm talking about this small RZ factor. This RZ is the incremental resistance in the reverse biased operation. Obviously, when the Zener diode has crossed its breakdown potential. Okay. And quantum mechanical tunneling of electrons has become effective. And what is VZ naught? VZ naught, it indicates the knee voltage, or the voltage at which the onset of this Zener breakdown happens to occur. The onset of Zener breakdown happens to occur at VZ naught. Okay. Now that has been made clear, and that is why it has been put up in a very linear kind of an equation, that VZ equals to VZ naught plus RZ into IZ. Because this is an incremental resistance, so we can put up with RZ and give a linear representation for the Zener voltage which gets developed effectively. Now look at this corresponding diagram, which gives you a far better picture of understanding the various components in the reverse breakdown operation. Now look at this diagram. In this diagram, what we are referring to? We are referring to the factor that VZ, this VZ is the test voltage of the Zener. Test voltage means what? The output regulated voltage that we are referring to, the value of V out. That is the fixed voltage. That should have been the picture. It will all, VZ is also going to vary. Obviously, it's going to vary if the VS and RL varies. But the variation will not be too much. It should be within a very small limit, very small range. And accordingly, far better DC outcome can be obtained, regulation. And the other component is this IZT. So this is the test current. So if you look at this diagram, if you look at this Q point, which we are referring over here, that is the intersection of this VZ and this IZT lines, which has been drawn from the x-axis and y-axis respectively. So that is the Q point. And if you now refer to the slope at that particular Q point, the slope at the Q point is going to give you the idea of the dynamic resistance or the incremental resistance of the diode. that is equal to RZ that we
Hello,
are
sir.
referring to. Yeah.
Excuse me. Sir,
Yes.
my mobile data is over for the day. Can I leave right now?
You can leave, not an issue. You can leave the meeting if it is so.
Oh, okay.
Okay, fine.
Okay, sir. Sorry to disturb.
Sure, fine. Let us continue therefore. So,
Sir, can I call VZ
uh,
not as
no, no,
threshold
no,
voltage for Zener
oh,
diode?
yeah. Yes, what is your question?
Sir,
Can you
can we
please?
call VZ? Sir, can we say VZ not is the threshold voltage for Zener diode?
Yes, threshold voltage we could have said, but we normally don't put it up as threshold voltage because by threshold voltage we mean, just a minute. By threshold voltage, what we mean is the onset voltage for current conduction in the forward bias. Though it is in some of the textbooks, you may find the threshold voltage has been mentioned in the reverse biased operation as well. It's normally being called to be the knee voltage. Threshold voltage, obviously threshold, it's definitely a threshold from the point of view of the reverse operation. But when we talk about threshold, we'll take into account the forward biased context of the diode. Otherwise, when we talk about this reverse bias operation, we are mainly considered about the factor knee voltage. So beyond the knee voltage, the current will sharply increase as being shown in the diagram according to the blue line. Okay. Now as I was talking about, the test voltage and current happens to be VZ and IZT. Fine. I have talked about VZ naught to be the knee voltage, beyond which if the voltage increases, it will lead to the context of breakdown and quantum mechanical tunneling happens to occur. So that is being shared in by two different points. Ultimately, in the realistic scenario, it happens to be same. Look at these 2 points, VZ naught and VZK. Two representations have been shown, VZ naught, VZK. What is VZ naught? If I just draw a particular tangential line at point Q, the point at which it strikes the x-axis, that is VZ naught. If you look at the diagram, have a close look at the diagram. If I just draw a tangential line at the Q point being shown in the diagram, okay, the tangential line crosses the x-axis at the point VZ naught. And the one, according to the description of normal Zener diodes, the onset of the knee voltage beyond which the current flow happens to occur is called to be VZK. Normally, these two values are almost same. Though shown differently, but they are almost same. So you can consider to be the same thing only. No need to worry about it. Okay. Rest of it is showing the fact, obviously, that the amount what the delta V is very small, delta I is very high, huge compared to delta V. That's fine. So this is the nature of the corresponding characteristics of a Zener. Now, let me get back to this structure, the one that has been designed for basic electronics.
So could you repeat the VZK part? That one I did not understand.
I will try to make you understand through the examples. Now, I should rather tell you one thing, that you refer to this slide because we should not spend the same idea twice. Okay. If you face any difficulty, you can definitely put it up in the MS Teams. You can chat with me and you can just put up a question if you have any query over there based on this slides. Okay. But I would like to explain Zener diodes from the basis from the analog electronics slide because that is far more understandable and far more clear from the practical point of view operation. Though I think whatever is being mentioned in this particular slide, in this case, is very much understandable. If you just follow the slides, you'll be able to get through. What the major point, three major points in this particular segment. I've been talking about page 22, page 23. If you can look, fixed VI variable RL, fixed VI variable fine, then fixed RL variable VI, page 24. And this particular example, page 25. Actually, and page 26 example of 25 only, page 25 extension. So these are the 4 pages which you are mainly going to refer. Okay. It is the same as what we are going to discuss. Yeah. Yeah.
The RZ is less than 1.
RZ is less than 1. That is obvious because you have to have a very small amount of resistance, right? Because the slope is excessively high. So it should be okay. Very small value.
Okay, sir.
Actually, what happens, to be more frank with you, the value of RZ is even lower compared to the forward bias context. Okay. Mane, if I talk about RZ, keeping in mind that RZ is applicable as the incremental resistance under reverse bias. Okay. So let's try to take up. You just follow. I am not saying that you don't follow. You do follow the ones which have been shown in this particular slide. Do follow. It has been clearly mentioned what are the paths of the flow of current and the various equations and all. Let's take up for the class discussion, the one from the analog electronics domain. Okay. So before I get there, let me just take up a case of a forward bias. Now, if you can look at the title of this particular slide is mentioned the diode as a voltage regulator. So both the cases have been considered, forward bias, reverse bias. Now, when we talk about reverse bias, we think from the point of view of Zener diodes only. Obviously not, we don't take into account avalanche multiplication in normal diodes because that will lead to excessive heat generation and the diode may burn out. So we avoid it completely under reverse bias regulation. But both the kinds of diodes are equally applicable from the point of view of regulation under forward bias as well. Definitely the level of regulation is not that good, but the point is this, it is possible. To explore that idea, you just go to this example on which I am highlighting right now. Whether I've highlighted. So let us say that you are having a 10 volt DC supply with a ripple voltage of plus minus 1 volt peak. That is the DC supply. Sorry, there is a DC supply. Okay, having a ripple of say plus minus 1 volt peak, and then you are trying to rectify that DC supply much better and getting a regulated outcome, making use of a diode. That is what I'm trying to figure out is this, that is you're already having a DC supply in hand. You're going to make or you are going to achieve a kind of a regulated supply which is even better, let us say, as a DC. So if you want to get into that kind of a design, what should be the way we can move through? So if you look at the example being quoted on the screen, let us have a 10 volt DC supply with a ripple voltage of plus minus 1 volt peak. What does it really mean? It means 10 plus 1, 11 and 10 minus 1, 10 minus 1, 9. So 9 to 11 volts kind of a ripple kind of a thing is going to happen. And we're having an average level of 10 volts. Okay, and that is the DC level. Fine. Now that induces a change of what? Let us now, as we all know, under forward bias also, even if it is a Zener diode or a normal diode, whatever be the kind of diode, the level of forward biasing voltage at which the current flow does occur and the forward current conduction is pretty appreciable, it happens to occur at the value of around 0.7 volts, as been mentioned. And let us say, according to the diagram as been considered in the case, that is R equals 10 kilo ohms and RD equals 27 ohms. What does it really mean? It means that R is basically the kind of a source resistance, okay, which is getting driven from the source, which is having a 10 volt DC supply with ripple plus minus 1 volt. And RD is the dynamic resistance of the forward bias diode, which is in series with the source resistance. So the concept is very simple. That is, you are having a source, over here, you are having a resistance, you are having a forward bias diode. Simple idea. This is the kind of a thing that we are referring to. Simple idea. So where we are having, let us say, forward bias. I'm talking about forward biasing. So the fact is this, if I talk about forward biasing over here for the corresponding diode, according to the diagram being shown on the screen. So what is the level of change that is getting encountered if you're having the dynamic resistance of the diode to be 27 ohms? The value is very simple. That is equal to RD divided by R plus RD into the value of 1 volt plus minus 1 volts, depending on which zone it is conducting. RD divided by R plus RD into plus minus 1 volt. Just multiply to that. So that will fetch you the idea about the level of variation that is getting encountered across the diode, because that is the ultimate story. That is, you are observing the output voltage across the diode. though it is very trivial, but the point is good to be discussed at this segment. So if you take up this particular formula and apply the values as been shared on the screen, you can get through the idea that the level of variation is 2.7 millivolts. So what is the diode voltage? 0.7 volts. Also, what is the variation? Plus minus 2.7 millivolts. What is the supply voltage? 10 volts with the variation plus 1 volt. So what is the variation? In the variation supply, the variation is around 10%. But at the output, the variation is around 0.4%. So obviously,
Sir, formula is coming RD by R plus RD, which is
Minor.
giving 2.7 millivolt peak.
No, that is, I'm simply applying voltage divider rule. I'm simply applying the voltage divider rule over here. All of you are quite aware of voltage divider rule. That is RD by R plus RD into VI plus
Okay, sir. Got it.
R by capital R by R plus RD into 0. Because if I talk about the negative potential over there, 0. So that segment is out. So we have only the first part of it. So if we move in this particular way, it is very easy to understand that the corresponding variation happens to be around 0.4%. So, sorry. So the factor is this, that the regulation is also effective if you put the diode under forward bias context. Though trivial, but it is effective. Now, the regulation context, obviously, when we talk about regulation, we do not mainly consider in the forward bias context. We take it in the reverse scenario, and that too, we're making use of Zener diode because regulation is far better. Okay. Now, let's quickly get into the elaboration of this Zener regulation through an example. Okay. Though I have not shared any numerical value, I have gone through only notation-based representation for the conceptual understanding of the corresponding scenario of Zener breakdown and all. Now, as being shared, that is what is given in the problem. That is VZ and IZT happens to be the test voltage and Zener. Sorry, test voltage and current across a Zener in the reverse bias context. Supply voltage is Vs with a source resistance Rs, okay, which can vary by what? Plus minus beta. Look at this factor, plus minus beta. That is Vs plus beta or Vs minus beta, indicating the variation of Vi. According to this old representation, I mean this basic electronics segment, what has been shown, according to this, we are talking about variable
Plus
Vi.
minus 1.
This one I'm talking about, variable Vi. The representation, the rectifier and regulator circuits of that slide which I'm showing right now, we have mentioned a fixed RL and variable Vi. I'm talking about this variable Vi segment. The variable Vi is effectively, according to in this particular example, to be in the form of Vs plus beta or Vs minus beta. Simple. Now that power supply voltage is going to supply the power to the Zener diode, and that Zener diode is in parallel combination with a load resistance RL. So what is the kind of a diagram? I do not need to draw the diagram because the diagram is already drawn in front of you. This kind of a structure. Simply, this is the kind of a structure that I'm referring to. There is a source resistance, there is a source resistance in the corresponding concept. There is a Zener diode which has been kept under reverse bias. Look at this polarity. Zener diode is under reverse bias. We put it into that assumption because we're talking about Zener regulation effectively. And we are having the load resistance RL over here. So this is the structure that we're trying to figure out. Okay. But this Vi is variable. This Vi is a variable factor. Vi is variable. Vi plus minus beta or Vs minus plus minus beta, which has been shared over here. Now, and the third given condition according to this example is the knee current is IZK. Knee current is IZK. Probably I missed out when I mentioned this diagram. That is the onset of the Zener breakdown over there. And the need voltage is VZK, which is approximately equal to VZ0, almost rather equal to VZ0. So that's it. And the increment resistance is RZ. So these are the standard given things in any Zener diode application. Okay. Now, what are we interested to find out? Actually, when we take into account Zener regulation, these are the four things which are of practical interest. The one which has been shared in the basic electronics base slide on rectifier and regulator circuits, that is from the book which you can find in any book actually. Okay. Everything is fine. That is okay. But practically what are the aspects that we need to keep in mind when we have designed a regulator circuit making use of Zener diodes is the one which we are going to discuss right now. Now, first thing is we need to find out what is the no load voltage. Next is the line regulation, followed by load regulation, and the most crucial factor, that is point number 4, the minimum load resistance in parallel to the Zener diode. Before even I get into the first 3, I would like to stress on point number 4. Though I will discuss point number 4 later on, but I would like to stress right now what point number 4 is all about. In short, minimum load resistance in parallel to the Zener diode. Why I am stressing on this particular part? Now, it is pretty obvious if the load resistance happens to be pretty low, it may lead to a context that the entire current that is getting driven from the source passing through the source resistance, the entire current flows through the load resistive path. And there is almost null amount of current passing through the Zener. Or it means that is the Zener diode is in this segment of its operation. It has not crossed VZK. It is less than VZK operation. Insignificant amount of current is passing through the Zener. So the corresponding output voltage will be far more variable depending on the load current, the variation of load resistance, because IL into RL is going to judge you what is the output voltage according to the diagram what I have shared. If this Zener is open, think about the fact that the Zener is open. I go back to this diagram. In this diagram, this particular Zener diode is open. This load resistance is very low. So the entire variation will depend on the factor of this whatever current is coming up from this source, okay, as well as what is the variation of RL occurring. So these two factors will contribute to the aspect what is the variation in the output load voltage. So we should be able to avoid that thing. That is why it is mentioned over here in this slide, that is the minimum load resistance. It should not go beyond a certain value of load resistance, because if it goes beyond that level of load resistance, then the effective aspect of designing this regulator circuit will completely fail. There won't be any effect of the regulation at all. Zener diode will not play any role, hence no regulation, zero regulation, complete failure of the circuit. So the resistive value should at least be higher than the minimum load resistive factor, which you find out depending on the values and specification sheets been given. So that is the point of consideration that we are going to go through under point number 4. So let us go step by step to find out the various components. So first thing is the no load voltage. Now if you look at the low load voltage, how to get this no load voltage? As being clearly mentioned, it is no load voltage. So do not put any load resistance, keep it open, simple. What are we after? What we have after is this, that is we know from the specification sheet of a diode of this particular Zener diode are also given over here. What is
Sir,
the
why
test? Yes.
no load voltage? Why do we have to find no load voltage?
I will tell you. That will come under point number 2 actually. Okay. Let's continue. That answer will automatically come up. Now the point is, when we talk about this no load voltage, we are disconnecting the load resistance RL and we are keeping up only the Zener aspect into the corresponding circuit. So according to the specification sheet, we have the idea of VZ, we have the idea of RZ, we have the value of idea of IZT. We all having all these 3 ideas are there with us according to the specification sheet also given in the given segment of this problem. So from there, applying this linear formula, which we have disclosed over here, applying this particular linear formula, we can directly find out what is the knee voltage for this Zener diode. So that is the value of VZ naught. We get that answer. So once we get the value of VZ naught, the knee voltage. So what is the value? We have IZ1. So what is the value of IZ1? IZ1 is the same amount of current which flows through source resistance as well. IZ1 is the same amount of current which flows to RS as well, because RS and RZ now are in series. Simple series connection with Vs being the corresponding source. So if the factor is this, that we have found out the value of Vz naught, it means what? That is, we are at the onset of understanding the breakdown voltage. That is why I have kept over here Vs minus Vz naught. Look at this Vs minus term. It is not any other value of Vz. It is Vz naught that we're referring to. Talking from the point of view of onset. So if I put up that thing and we take in that particular current, that corresponding current comes to equal to Iz1. And if I put up that particular current in the corresponding operation, we get the no load voltage across the Zener. Now, as I was talking,
Why
now as
we
a
subtract it?
subtracted, why? Why not?
Why Vs minus Vz not?
Look at this circuit. Look at this circuit now. This part,
Yeah.
no load, no load. No load means you open this load and then you refer to this circuit. Vs is actually referring to this Vi according to this diagram. Okay. And Vz naught is the corresponding potential onset or the knee potential of the corresponding Zener diode that we have right now find out applying the linear formula. So if I apply Vs minus Vz naught divided by this Rs plus Rz, we get the idea of this what is the amount of current through Zener. Look at this part. What is this representation of the Zener? How do you represent the Zener? We effectively represent the Zener like this. Look at this representation. Now I don't think there should be any confusion. Vs minus Vz naught divided by Rs plus Rz. This part is clear. Look at this representation of Vz. Then the idea will be clear. Rs will come in series with Rz, and there are two potentials. One is Vs, other one is Vz naught. So in effect, that is the true story. And then if you apply the polarities and all, you get the value of your Iz. Okay. So once we have the value of Iz, which is the same current flowing to the source resistance as well, we have the no load voltage across the Zener to be equal to, as being shown, Vz naught Rz into Iz1. Fine. Okay. Now, the question that someone asks that about the necessity of this no load voltage and all. Well, there are two prime aspects that we need to get through. One is called line regulation, other one is called load regulation. What is the line regulation factor of the Zener and what is the load regulation factor of the Zener? This is an important thing over here. So if I talk about the line regulation, look at the formula which has directly been applied to make you understand what line regulation is all about. Look at this formula. This formula is trying to give you an idea about if there is a change in the source, what is the amount of change that you encounter across a Zener? If there is a change in the source, what is the amount of change that you can expect to encounter across a Zener? So that has been clearly being mentioned to this formula. Plus minus beta. If you look at the primary, if I consider beta to be equals to 1, put beta equals to 1. So it should be plus minus 1 factor multiplied to Rz by Rz plus Rs. Just applying voltage divider, nothing else. You get the idea of line regulation.
Sir, now please leave, sir, because sir, today we have 8 hours of class.
Now I have to,
Hectic,
no, I understand. I truly understand your pressure, but let me finish off this segment because okay.
Okay.
So we are having therefore the line regulation is that particular concept. So we have the idea about the change in the output voltage across a Zener corresponding to the amount of change present at the input level, Vs. So that is all about line regulation. And from where we have the idea what is the significance of no load voltage and all, that is clearly understood. Coming to the other half, that is load regulation. Now let us try think in a very simple way. Whatever be the amount of increase of current through the corresponding load resistance, if we assume that the every voltage factors, I mean the input voltage factor is some at some particular level. Okay, so if whatever be the increase in the load path, obviously the same level of decrease should happen in the Zener path. Isn't that so? Try to understand the fact. If the source is fixed, current is fixed to the corresponding source resistance, then if you apply a load resistance, so whatever be the increase of the current flowing through the corresponding load path, a same level of decrease is expected to occur to the Zener path. So that effectively the sum up of the two happens to be the current flowing to the source resistance, which is the old value. So that is the thing that is all about in load regulation in a very simple way. So the current flow through RL is, let us say, 1 milliampere. So in effect, it means that if the current flow through RL has increased from 0 to 1 milliampere, the current flow through this Zener will decrease by the same amount of factor, if we assume that is the particular context of the current. So therefore, the output voltage is going to have a variation that is equal to what is delta V? Delta V is equal to delta I into RZ. What is delta V? Delta I into RZ. Delta V is equal to delta I into RZ. So we have just applied that idea. So what we have understood, we have got the value of delta I across a Zener, multiply that level to RZ and get the value of delta V. And that delta V is all about this load regulation, because we have connected a load resistance RL. Now the most crucial part, after which we will end up our session today. So minimum load resistance, how do you get to that? Let us say that you have connected load resistance in a Zener circuit in operation, which is very low. Now you have to understand whether the load resistance is applicable in Zener regulation or it is not applicable. So it is a two-step process. So in the first step, what do we understand? Let us say that the value of RL is equal to R low. Okay, let us say. So the current flow through R low should be equal to what? If we have this idea that the Zener regulation was going proper, that is, Zener regulation means what? That the output voltage will remain fixed at Vz. So whether there is a change in the RL factor or VI factor, output will be more or less fixed at Vz. So if that is the concept, so in this case, if we think from the point of view of the fact that is you are decreasing the load resistance, what will happen? So the current flow through this R low, if the output voltage is Vz, then regulated output voltage Vz should be equal to Vz by R low. So Vz by R low is equal to the current flow through R low resistance. What do you need to check? You need to check about this inequality. That is Vz by R low, whether it is greater than Vs minus Vz by Rs. What does it really mean? It means that if by applying this particular values, if you find that this value happens to be greater than Vs minus Vz by Rs, that is not possible. Obviously, the current flowing through the load resistance will be a component which is coming from the source. It cannot be greater than the source current. The one that has been shared on the screen to this equation shows the fact that the component current is becoming greater than the source current itself, because the right hand half of this inequality is indicating the source current, and the left hand half of the inequality is indicating a component current, and that through the load resistance factor. So that is not possible. Otherwise, the Zener diode, if this thing really happens, because it does happen. If it does happen, if the value of R low becomes too low, if it does happen, it means that the Zener diode has come to its non-conducting state. Zener diode is not conducting in the reverse biased operation anymore. So it's in the non-conducting state. So had it been the conducting state, then this thing shouldn't have been possible. This thing is only possible if this Zener is in the non-conducting state. So in that case, if the Zener becomes non-conducting, then we can understand the output voltage should be simply a voltage divider rule. R low by R low plus Rs into Vs. Zener diode is out from the picture. No regulation, nothing. There is no regulation at all. The entire regulation has failed. So how do you find the minimum value? So from phase 1, it is clear that RL has to be greater than R low, so that a minimum current flow is maintained to the Zener diode IZK, the knee current. That has to be ascertained. That is the minimum level of current IZK has to flow through the Zener. Otherwise, it will come to phase 1. We do not want this operation in phase 1. We want the operation in phase 2 and higher, not in phase 1 definitely, if we are in the regulation scenario. So when we talk about the knee current, so what is the worst case current? Look at the source voltage, Vs minus beta. Vs, I'm talking
Sir, why
about,
minus beta?
yes, I'm talking about the worst case current drawn from the source. Worst case. One is Vs plus beta and one is Vs minus beta. That is what is the minimum possible level of current that we are referring to. So to get into that idea, obviously the minimum voltage that is getting applicable from the source end, we should take that thing into consideration from the practical point of view. So we have Vs minus beta, not Vs plus beta. That is why I'm mentioned over here as the worst case current drawn from the source. That is corresponding to Vs minus beta. So Vs minus beta, now it should be at the onset of conduction. Vzk, and that leads to Izk. Okay, that means you are at the onset of the Zener conduction and the Zener path is on. It's no more open. Okay, and the regulation is working fine. So if to get into that particular onset, I'm just talking about the onset. How do you get to that particular concept? So the step 1 in the phase 2 indicates Vs minus beta minus Vzk by Rs. Onset I'm talking about. So we talk about the knee voltage. We know the knee voltage. So get the worst case. What is the worst case current drawn from the source? So what is the current through RL? Current through RL should be equal to the one that we have obtained over here minus the value of Izk, because the current for the onset of the Zener in the reverse bias scenario is Izk. So the current that we have obtained in step 1, from that level of current we subtract Izk. So that will be the amount of current that should flow through the load resistance RL. And based on this idea, we can find out what is the minimum value of RL that should be connected. It should not go beyond that, lower than that. If it goes lower than that, then you are back into phase 1. And sorry, if it is lower than that, then you are back into phase 1. It has to be greater than the value of RL. Minimum value of RL has been quoted over here. It's pretty obvious. That is, the value should be equal to as being shown on your screen. It is the current through RL that we observed. Okay, so that current through RL by VZK, simple. So what is the minimum value of RL that we are referring to? So this two ratio of these two should give you the minimum value of RL. Because I have considered the worst case current to begin up with. So the minimum value of RL should be the one as being shown on the screen. You can take up some practical values and get into the particular analysis. But the idea is this: how do you find out the minimum value of RL? To understand the regulation is at its onset and it is working fine. Okay. And before we end today, just one last point that I need to share with you, all of you. That is, sometimes we do make use of Zener diodes in series with normal diodes. How come? That is, the normal diode is under the forward biased mode of operation. And if it has been already been discussed in the class, I have not discussed, but it's a part in the diode segment. Obviously, it should be discussed. So a normal diode in the forward bias scenario has got a negative temperature coefficient of resistance. Sorry, negative temperature coefficient, which is equal to minus 2 millivolts per degree centigrade. Normal diode under forward bias. Now, if you connect a normal diode under forward bias with a Zener diode in series, but the Zener diode is in reverse bias. Normal diode is in forward bias, Zener diode is in reverse bias. They are in series. If that thing kind of a combination you develop in any kind of a circuit, and the add-on information is this, that the Zener breakdown is having a voltage greater than 5 volts. In that case, what we encounter is this, as being mentioned, clearly mentioned on the screen, that the Zener breakdown incorporates a positive temperature coefficient above 5 volts. If it is having the value of VZK above 5 volts. If the value of VZK is less than 5 volts, then it is having minus 2 volts, same as the normal diode. But above 5 volts, it comes to plus 2 millivolts per degree centigrade. So if you just connect these two things in series with Zener in the reverse bias context, having a breakdown voltage higher than 5 volts, or the knee voltage is higher than 5 volts over there, in that case, it means the two will come in series and effectively minus 2 and plus 2 will cancel each other. And the corresponding diode will exhibit a zero temperature coefficient. It will exhibit a zero temperature coefficient. The thing will not change with temperature. The voltage will not change with temperature. It's a very crucial and interesting thing of connecting these two diodes in series. A Zener with a normal diode, provided the Zener diode is having a breakdown potential higher than 5 volts. Now your question, please. Any question you are having? Anyone?
Could you repeat
The
why
I
that
zero,
was
sir.
not plus
Sir, forward bias diode will have a temperature
No, no,
coefficient.
no. I'm talking about zero. No, no, no. The forward bias diode. Let me tell you like this. That is, I can draw over here as well. This is the forward bias diode, let us say, and this is your Zener diode. I'm talking about the. No, this is a problematic thing. Just a minute. This is the Zener diode. No, it has started playing with me. So plus minus. So what has been shown over here is effectively giving the idea that this is the forward bias diode having minus 2 millivolts per degree centigrade temperature coefficient, and this is the reverse bias Zener diode which is having plus 2 millivolts per degree centigrade. If the Zener diode's VZK is above 5 volts and these two are in series, in that case the combination of these two in effect will have a zero temperature coefficient. That is, the voltage will not change with temperature if you connect these two in series, provided the Zener diode is having breakdown potential above 5 volts. That was the point. Okay, so now if anyone else is having any question or any different form of question, you please go ahead.
Kindly repeat why that was not plus beta.
Why not, Duster? Look, if I take into account plus beta, what should it really mean? It should really mean that we are having more amount of current. I'm talking about the worst case current and the minimum value of RL. When we are talking about the minimum value of RL, we are talking about the what is the worst case current drawn from the source. Worst case current means exactly what? It exactly means that is what is the minimal current. What is the minimal current that can be drawn from the source? If plus minus beta is the variation of Vs, that is the source supply, so the maximal current should be dependent on the fact Vs plus beta, and the minimal current depending on the equation given in step 1. Depending on the equation given in over here in step 1, the maximal current will be applicable if we have Vs plus beta, and the minimal current will be applicable when we get into the concept of Vs minus beta. Rest part of it is just getting the idea of putting in the concept of the Zener into force or the Zener regulation in effect. So when we talk about that least amount of current or the minimal amount of current that can be drawn from the source dependent on the variation of beta, then it should be Vs minus beta minus Vzk divided by Rs. Isn't that the story? Because Vzk should be the potential across the output. Vzk is the potential across the output. That is the regulated potential, the regulated DC value that you are expected to have should be equal to Vzk. The regulated DC outcome should be expected to be equal to Vzk according to phase 2's description over here. Obviously that will also change, but the change will lead to level of Vz. From Vzk it will lead to Vz. Vzk, let us say, let me give you a very practical example. Vzk will be of the order of, let us say, 6.3 volts, and the Vz is of the order of 6.7 volts. It's not too much of a difference. Okay. So that's the point. So if you apply this minimal level of current, then you start off from step 1. Then you find out what is the current through RL, obviously. Obviously, we know the value, what is the current through the Zener, that is IZK that we're referring to. So the minimal current component that is going through RL should be equal to the one given in step 2. And from there, we can understand what should be the minimum value of RL be. Applying the formula's extension only. Just V equals to IR. Applying V equals to IR, we're getting step 3, the minimum value of RL. So this is a very practical and concept, a practical and problem which I have discussed with you all. Otherwise, I would like to share one more thing, that is this thing you are going to study fine, but you are also requested to study this material as well. it has got a different approach of making you understand the Zener, the maximal and the minimal current and everything. But in effect, the concept is same. It is not having any difference. If you are facing any difficulty, you please do mail me, or you can contact me through in the chat in MS Teams. I would answer you, not to worry about that. Okay. So that's all for today. So if you have any further question, you can go ahead. Otherwise, we have finished up with this. We have finished up with this Zener and all.
Post both these materials in the MS Teams.
Both are there. No need to worry. Both are there.
Okay, so the analog and the basic one, right?
Both are there. Both are there. Both are there. No
Okay,
need
so
to
thank
worry.
you.
Sir, the next class will be on Wednesday or Thursday.
Just a minute. For the first question about the class, I think on 26 January, if I take a class, it will not be good. It is not good to take class on 26.
Legally, it's not good, sir.
It's not good, obviously.
Sir, you can take, sir. Sir, we don't have any class, sir. So we don't have any
sir,
class.
don't check, sir. It is
Just
too
a minute,
stressful.
At night,
Right?
sir.
Today
At
is too
night.
stressful.
No. You please
Sir,
stop.
Wednesday
Don't
evening
take,
will
sir.
be
Let's have.
will
Please don't
be
extend.
helpful
Please
to
stop.
us because we have no class. So
You please
Today it
stop.
is too
You
stressful.
please stop. You please stop. We will have the class in that case on Thursday. Not an issue at all. We'll have the class on Thursday, followed by on Friday. Finished. Matter ends. Forget about Wednesday. We'll have it on Thursday, followed by Friday.
okay.
At same time,
Thank you,
7 p.m. Okay.
Thank you.
So
Sir.
let me just take that. And yes, any question?
Sir, the minimum value of the resistance, sir, it is like the shortest less resistance path of the current.
Obviously, if you know, for example, it's a very good question, though it's understandable, pretty understandable. Like if you put the value of RL to be equal to, if you short this resistance RL, let us say, if you short the resistance, if we just go for a short across this Zener, then will the Zener work?
No, sir, the Zener will be eliminated.
Eliminated. Completely. Zener will not come and have its effect at all. So that is the story. So you should have some minimum level of RL for the action of the Zener. If it becomes lower than that, Zener will fail and this equation will have its effect, which is a problem. This equation will have its effect, which is a problem. That is, the component current cannot be greater than the source current. If that thing gets into the picture, that is by default, it's bound to come. It's bound to come. If you take up the corresponding values, you will get into this kind of an answer that the component value has become greater than the source value. That is not possible. Definitely not possible. So if that thing kind of a thing is getting into the context, then it means that the concept of Vz is not at all there. We are applying this concept of Vz over here in this equation, but this concept of Vz itself is not there. So this equation doesn't carry any meaning over there under step 1. So in that case, we have to refer to the context of normal voltage divider, and the Zener regulation is completely out from the picture. So that is the point, in short.
Okay, so sir. Thank you, sir. Understood.
Okay then. So that's all in that case. If you do not have any further question, it's already 2019. So I should either stop now. It's too late.
Okay, sir.
Yes, sir.
It's just too late.
Thank you, sir.
Just thank you. Just a minute.